A high-pass filter. One application of LRC series circuits is to high-pass or low-pass filters, which filter out either the low or high-frequency components of a signal. A high-pass filter is shown in figure where the output voltage Vout is taken across the LR combination. The LR combination represents an inductive coil that also has resistance due to the large length of the wire in the coil. Derive an expression for Vout divided by Vsource, the ratio of the output and source voltage amplitudes, as a function of the angular frequency omega of the source. Show that when omega is small, this ratio is proportional to omega and thus is small, and show that the ratio approaches unity in the limit of large frequency. So in this circuit, let's take this as our reference direction for the current, although the current is oscillatory. And we're looking at output voltage across the inductor and resistance R, and resistor with resistance R. And we also have a capacitance connected in series. To analyze this circuit, I have to note here again, once again, that the resistive reactance is resistance R, inductive reactance is omega L, capacitive reactance is 1 over omega C. And for the resistance inductance combination, so this is my phasor diagram. The inductance is making 90-degree angle with respect to the resistance, and the capacitor makes a minus 90-degree angle because of the phase difference between the current and the voltage across these circuit elements. So here I have the 90 degrees for the inductance, and here I have the 90 degrees for the capacitance, minus 90 degrees. So if I write the impedance of the resistance inductance combination, so ZRL will be just the combination of these two without the capacitor here. So it will be XL and XR. So it's going to be XR square, which is R square, plus XL square, which is omega square L square, square root. And for the overall impedance of the circuit, I would have XL minus XC squared plus R squared inside the square root. Now the source voltage Vs is going to be equal to the amplitude of the current multiplied by the impedance Z. So it will be I times XL minus XC squared plus R squared square root. But for the output voltage, on the other hand, I can write Vout is equal to the current multiplied by the impedance of the resistance inductance combination. So it is I times square root of R square plus omega square L square. Okay, so now I can write Vout divided by V source. So let's do that here. Vout amplitude divided by the source voltage amplitude. This is the ratio of ZRL to Z, as you can see here, ZRL to Z ratio, which is R square plus omega square L square square root divided by omega L minus 1 over omega C parentheses squared plus R squared square root. So that's basically the answer for this question. Here I can put this in a box. Now let's analyze the behavior in the limit of low frequency and high frequency. What happens to this ratio in the limit omega approaches 0? That's the low frequency limit. The ratio of output voltage and the source voltage. Now, if I substitute here, omega is equal to 0, this is going to become square root of r squared, which is simply r. And if I go down here, I substitute omega is equal to 0 here, so this is going to disappear. If I substitute omega is equal to 0 here, this term will blow up. So 0 minus 1 over omega c parentheses squared, so it will blow up. So it will be 1 over omega c parentheses squared, and it will be much greater than r. So therefore, I can substitute here 1 over omega squared c squared inside the square root, and that will be simply omega r c. So it's linearly proportional to the angular frequency. What happens to this ratio in the limit of high frequency? Omega becomes infinite. So ratio of the output voltage to the source voltage. If omega becomes infinite, you can see that this r will be negligible compared to this term. So I will have square root of omega square L square remaining, which will give me omega L on top. At the bottom, as omega goes to infinity, this term becomes 0. As omega goes to infinity, omega L parentheses squared will be much greater than r squared. So that will replace r squared. So I will have omega L parentheses squared inside the square root. So this will give me simply a ratio of 1. So high frequencies will be passed without any attenuation, but low frequencies, at low frequencies we will have an output omega RC times the V source, so it will be attenuated. So this is going to act as a high-pass filter. So in this question, we have a high-pass filter. The output voltage is taken from the RL combination, and there is a capacitor connected in series, and then we have a V source. This RL combination actually represents a single inductor with a large coil resistance, R. So when omega is small, the ratio should be proportional to omega, thus small. And when the ratio approaches unity, that's the high frequency limit. So we have shown that in the omega infinite limit, it becomes 1, no attenuation. As omega goes to 0, the output goes to 0 as linearly with omega. So we first look at the reactances of these circuit elements, R, omega L, and 1 over omega C. The combination of RL has a reactance R square plus omega square L square square root. The overall impedance of the circuit is XL minus XC square plus R square square root. So that's basically found by this phasor diagram. So source voltage is I times the impedance of the circuit. Output voltage is I times the impedance of the RL combination. So the ratio of output to source voltage is the ratio of these two impedances, ZRL to Z ratio. So we have shown that as omega goes to 0, the top becomes R, the bottom becomes 1 over omega C parentheses squared. So the end result is linearly proportional to omega. If omega goes to infinity, this term dominates, the top becomes omega L, and here this term dominates, it becomes square root of omega L parentheses squared, so the ratio approaches unity as expected.